Good afternoon, everyone. This is the pre-launch news conference for TDRS-K, NASA's Tracking and Data Relay Satellite, to be launched on Wednesday aboard an Atlas V rocket built by United Launch Alliance. And in our briefing today, our participants, leading off, will be Badri Yunus, the Deputy Associate Administrator for Space Communications and Navigation at NASA headquarters. Tim Dunn, the NASA Launch Director from the Kennedy Space Center. Vernon Thorpe, the Program Manager for NASA Missions from United Launch Alliance in Denver. Jeffrey Gramling, the NASA TDRS-K Project Manager from Goddard Space Flight Center. And Joel Tumbiolo, the Launch Weather Officer from the 45th Weather Squadron at Cape Canaveral Air Force Station. And we'll begin our briefing with opening remarks from Badri Yunus. Badri?
Thank you, George. I would like to mention that there are two critical functions and essential functions without which space exploration and all kind of science that we do in space wouldn't have been possible. These are the launch services and the space communication and navigations. These two functions, if you don't have and you don't perform them successfully, you cannot do any science or human exploration in space. Space Communication Navigation SCAN is the program office at headquarters responsible for all NASA space communication navigations. I'm the Deputy Associate Administrator, and I'm also the Program Manager for SCAN. I have a few slides to show you to explain a little bit about our program and the value we add to the nation. First slide. Second slide. SCAN is a very intricate and complex program. We have assets all over the world providing communication and navigation services to a whole wide variety of space users. And they can vary from suborbital users all the way to users who are now presently crisscrossing the boundaries of all our solar systems. We have three separate networks that have evolved independently over time, catering to the specific needs of the various missions. These are the Near-Earth Network, the Deep Space Network, and the Space Network. Next slide. At any day, we support over 100 missions. Anything you see coming from space has to go through us, has to be enabled by us. And these are the kind of missions, coded per the network that provide that support. Sometime two networks may be providing support to the same mission. And I will talk about the specific networks. Next slide. The support is provided to the human spaceflight as well as to robotic missions, whether you are doing astrophysics, heliophysics, whether you are doing space research in general, Earth exploration science. It has to go, and it will go, and it's all enabled by SCAN. Next slide. The Deep Space Network essentially supports users that are far away from Earth. And their main characteristic is that they have been designed to look for faint signal. Imagine a user having a 100-watt transmitter. What's 100 watt? Like a light bulb you have in your home. The further you go away, the less you can see it. Imagine you are yourself billions of miles away. We have the kind of capabilities, antennas, that can detect these signals and bring it back to the user to make sense out of it. The Near-Earth Network essentially caters to missions that are flying around Earth. They are primarily Earth exploration system, studying the weather, studying all kinds of sciences that are of interest to us on Earth, about drought, about flooding, about all kinds of things that we do on Earth. And it has also evolved over time, and it's an example of efficiency because We do rely on a hybrid model where, in addition to the NASA assets, we get also support from commercially provided services. The space network is the newest of all of the networks, and it has evolved over time based on a need to provide near real-time communication to our users. You know, as you go in space, the further you go, the more visibility you have to the Earth. But for those missions who are flying very near Earth, you know, because they go over ocean and land, it's tough to provide continuous coverage. I can give you an example. Next slide. The space network, before getting into the example, out of 9 spacecraft we had in orbit, we only have 7 who have survived. The 2 spacecraft that have been retired recently, although they have outlived their expected life expectancy, they failed, and so we had to put them in a retirement home in an orbit far away from our operating orbit. And we continue to rely on the remaining spacecraft, but many of them are getting old and they need to refurnish, you know. So that's why we will be flying the TDRS-K and the following TDRSs. Next chart. Operationally, we need 7 spacecraft, 6 operational and 1 hot spare, just in case one fails. We move it there and we'll continue to support our users. But the concept started in the 70s for the space network, where in order to provide, sorry about that, in order to continue to provide continuous coverage, we had to move away from the old model where we had so many stations distributed worldwide, along with ships and airplanes. The cost was very high to the agency. Additionally, it only provided 15% coverage. We could do more, so we came up with the concept, and it took us a while to implement it in the 80s, where the kind of coverage has increased to the 85%. By putting data relay satellite in a geosynchronous orbit, looking down on Earth, we were able to see, you know, much of the activities down under the geosynchronous orbit, and in the process, reducing the cost and moving away from the dangerous situation where we had to operate previously in dangerous part of the world. The geopolitical situation, you know, was such that, you know, that the cost was high and there were danger associated with accomplishing that mission and providing that support. Next. So we kept on evolving the network, and we added another capability to close a zone of exclusion. Although with 2 spacecraft you can see most of Earth, there was a small sliver that you could not see, and that was about 15% of coverage for altitude below 1,200 kilometer. By putting another station at Comm, we were able to close that zone of exclusion. The success we had with TDRS, you know, made everyone come to us for support. You know, all of the NASA mission wanted to be supported by TDRS. At the beginning, we wanted it to be to cater to those who required near real-time support, such as the human spaceflight. But when all of the other users saw the value, our requirements started to increase, and we had to add more spacecrafts. Next slide. That's what the example I was referring to. As you can tell, without a TDRS, the green area, the green spots that you see are the only coverage areas. The rest of the time, you know, the spacecraft was in the dark, you know, we couldn't communicate with it. Now, with the addition of TDRS, next slide, we provided that 100% coverage. Next slide. Again, our need is based on the requirements that we have that are required in the 7 spacecraft, and we keep on furnishing new spacecraft to replace failing one. And we expect that the requirement to go down between starting in 2016, but and we see more spacecraft failing, but we most probably will be moving from a 7 spacecraft operation to a 5 spacecraft operation based on the requirements that we'll be having in the future. And we don't see any need to any spacecraft beyond K and L and M that we are launching over the next few years until 2022. We are doing reliability modeling now to see how soon do we need to build the next generation of data relay satellites. Next slide. Again, all of the beautiful images, whether you are looking deep into space, trying to discover the origin of the universe, looking at the galaxies, or looking at Earth, trying to see the trend in the weather and the changes that are taking place. Looking at also providing support to the space station. All of the voice and the data and the video that you are getting that go through SCAN, without which if SCAN didn't exist, you wouldn't see any of the things that you are seeing. Science couldn't be performed as we know it today. Probably NASA, you would have seen a different NASA if NASA could exist without. Next slide. We have a lot more information on the website, and it's given to you over there, but I will be more than happy to take your questions later on.
All right, thank you, Badri. And now to our NASA Launch Director, Tim Dunn. Tim?
Thank you, George. I'm proud to be here today representing the men and women of NASA's Launch Services Program, and I'm thrilled to be the Launch Director for the TDRS-K mission. As Badri mentioned, the voice and data communications of TDRS constellation bring back to Earth every day from the International Space Station, the Hubble Space Telescope, and many of our NASA science spacecraft. It touches each of our lives. Working alongside our United Launch Alliance colleagues, the engineers and analysts of NASA LSP take great pride in readying TDRS-K to join this constellation. NASA has a terrific record flying on Atlas V. We've successfully launched 7 missions on this rocket, missions to Pluto, Jupiter, the Moon, the Sun, the radiation belts, and 2 spacecraft to Mars. TDRS-K will be the 8th NASA mission on an Atlas V and the 35th Atlas V overall. TDRS-K will launch on the Atlas V 401 configuration vehicle from Space Launch Complex 41. Slick 41 is proud to have hosted 29 Atlas V launches to date. Now I'd like to show a video of the ULA crew building up the Atlas V launch vehicle and mating the TDRS-K spacecraft at Slick 41. Please roll the tape. Here's a nice shot of the Mariner ship that transports hardware from the ULA factory in Decatur, Alabama. This is a shot of the TDRS-K second stage Centaur being offloaded here at Cape Canaveral Air Force Station and transported to the ASOC for ground testing. A beautiful shot of the Antonov aircraft. The Antonov is used occasionally by ULA to transport the rockets, both the Centaur and the first stage. Here you see the TDRS-K first stage being offloaded at the skid strip at Cape Canaveral Air Force Station and being transported over to the same facility as Centaur, the ASOC, the Atlas Space Flight Operations Center for ground testing. Here we are early on the morning of January 3rd in the fog out at the VIF near Slick 41, erecting the first stage onto the mobile launch platform. You see the professionals of United Launch Alliance connecting the overhead crane from the VIF and putting the first stage booster in the vertical position. You see the first stage engine there, the RD Amros RD-180 engine, thrust of 861,000 pounds, being lowered down onto that MLP. On Saturday morning, on the 5th of January, we brought out the second stage, the Centaur, rolled it from the ASOC out to the VIF for the same erection activities as the first stage. You'll see the erection sequence beginning here with the attachment, and the second stage Centaur is powered by the Pratt & Whitney Rocketdyne RL-10 engine with a thrust of 21,900 pounds. You see it being carefully positioned onto the forward end of the first stage and lowered and mated into position. And here we are, just over a week ago, the early morning hours of January 20th, the TDRS-K spacecraft, encapsulated in its payload fairing, left the Astrotech payload processing facility in Titusville and made its way out to Slick 41 at the VIF for mate to the Atlas V launch vehicle. You see the encapsulated assembly being lowered down onto the forward end of Centaur and mated. The TDRS-K launch campaign has gone very well to date. Over the past week since that TDRS-K mate, the Atlas V team has been busy with launch preparations. Last Tuesday, on the 22nd of January, we performed the final integrated systems test with the spacecraft and rocket together. Last Thursday, the combined NASA and ULA launch team held the flight readiness review, where we assessed the preparations and readiness of the Atlas V vehicle, range assets, and the TDRS-K spacecraft. Last Friday, we performed a mission dress rehearsal to exercise and prepare the entire ULA, Air Force, and NASA launch team. This morning, we conducted the launch readiness review for the TDRS-K mission. Senior managers from NASA Kennedy Space Center, Goddard Space Flight Center, and NASA headquarters, as well as ULA and the Air Force, assessed the readiness of the rocket, the spacecraft, and all range assets to proceed with launch on Wednesday evening. Tomorrow, we'll begin our final launch preparations at approximately 10 a.m. Eastern Time by rolling the Atlas V vehicle on its mobile launch platform approximately 1/4 mile north from the VIF to the launch mount at Slick 41. We'll then fill the first stage fuel tank with highly refined kerosene known as RP1. On Wednesday, the launch team will begin arriving on console in the afternoon hours Eastern Time. The crew will perform all final preparations for vehicle power on and electrical checks beginning in the afternoon hours about 1:30 p.m. Eastern. We'll follow that later in the day about 6 p.m. with cryogenic tanking of first stage liquid oxygen, as well as the second stage Centaur liquid oxygen and liquid hydrogen. Final engine slews will be performed after tanking, and then we'll be ready for launch Wednesday evening at 8:48 p.m. Eastern Time with a 40-minute launch window. In summary, the Atlas V rocket and range equipment is ready, and the combined government and contractor launch team is prepared and excited to launch this critical national asset, the TDRS-K spacecraft. Back to you, George.
Thank you, Tim. And now to Vernon Thorpe, the Program Manager for NASA Missions from United Launch Alliance. Vern?
Hey, thank you, George. ULA is honored to be here today, just 2 days from the launch of the TDRS-K satellite. Since we began building this vehicle in Decatur, Alabama, nearly 2 years ago, and through all of the engineering, the production, and all of the processing down here at the launch site, we worked with NASA and our other mission partners to get us to this point, and on Wednesday to a successful launch. The vehicle that will launch TDRS-K was prepared in just 27 days from its arrival at Cape Canaveral Air Force Station. That's a record processing time for an Atlas V vehicle. When the Atlas V program started, a typical processing time was on the order of 60 to 90 days. And as the team gained more experience, we were able to get that down to as few as 44 days in the past. The 40% reduction down to 27 days was possible due to the continued growing experience of our team, and also the results of a major initiative in 2012 to reduce processing time without adding any technical risk. We called this initiative Launch Span Reduction, and it offers our customers added manifest flexibility to meet their schedules, and it also offers additional launch opportunities to ensure that payloads can be launched on time and reliably. In fact, as a result of reducing our span times, we were actually able to insert an additional mission into our 2013 manifest. TDRS-K will be the first of 13 ULA launches planned in 2013. As Tim mentioned, it'll be the 35th Atlas V mission. It will also be the 67th mission that ULA has flown to date. This mission will be launched aboard an Atlas V 401, which uses the 4-meter metallic payload fairing. It has a booster powered by an RD Amros RD-180 engine, and the Centaur upper stage will have a single Pratt & Whitney Rocketdyne RL-10A-4 engine. This mission will not require the use of any solid rocket boosters. And now I'd like to show an animation that will give you a preview of what we expect to see on Wednesday evening. That's what the Atlas V 401 will look like on the launch pad. And at liftoff, the booster engines will generate almost 900,000 pounds of thrust to get the vehicle off the ground. And for this configuration without SRBs, the first major event that you'll see during the flight will be about 4 minutes in, when we've depleted the propellants in the booster stage and we shut down the booster main engine. You'll see that coming up here shortly. Once we shut down the booster engine, we'll separate from the Centaur upper stage about 6 seconds later, right there, and we will begin preparing for the first of 2 Centaur main engine burns. The first burn for this mission will last approximately 14 minutes. 10 seconds into that burn, we'll jettison the payload fairing, since we're pretty much out of the atmosphere by that point. And that 14-minute burn will put Centaur with the TDRS spacecraft into a highly elliptical orbit. The perigee will be about 99 nautical miles, but the apogee at that point will be over 13,000 nautical miles. Following that first burn, we'll coast for 82 minutes, then we'll do the second burn that you see here. That second burn will only last about a minute, and that will put us into a geosynchronous transfer orbit. 6 minutes after that second burn, we will reorient and separate the TDRS spacecraft. Total mission duration up to that point will be about 1 hour and 46 minutes. And then following that separation event, we will perform the normal contamination and collision avoidance maneuver and put the Centaur into a safe orbit so there's no chance of recontact with the spacecraft. ULA is proud to serve a critical role in delivering NASA payloads to orbit, and we're focused on perfect product delivery for this and every mission we launch for NASA and our other customers. Our focus is on successfully delivering important capabilities to orbit. Launch is just the beginning of this satellite's journey, and the addition of TDRS-K to the overall constellation will continue the successful legacy of the project and strengthen NASA's communication system that's so vital for the International Space Station and many other satellites that are in orbit today and will be in orbit in the future. In fact, even the rockets that launch these satellites rely on the TDRS constellation for receiving and returning the telemetry data to help us understand how to make these rockets function even better in the future. Once again, I'd like to say thank you to all of our mission partners, and with that, I'll turn it back to you, George.
All right, thank you, Vern. And now to TDRS-K. And to discuss the satellite is Jeffrey Gramling, the NASA TDRS-K project manager. Jeff?
Thank you, George, and good afternoon, everyone. We're very excited to be here this week to launch the TDRS-K satellite. This will be the 11th TDRS satellite that we've launched, but it's been a long time. It's been 10 years since we launched the last one. We launched TDRS-H in 2000 and I&J both in 2002. HIJ and the KLM series of spacecraft have all been built by Boeing in El Segundo, California. So we arrived at the Cape about December 18th, and I've got a video here to show you what's transpired since we've gotten here. So if we can roll the video. So what you see here is the spacecraft was flown on a C-17 provided by the Air Force, and it landed at the Kennedy Shuttle Landing Facility, and we're offloading here. And that's the shipping container, which was then taken to Astrotech in Titusville, where we did spacecraft processing, which included testing, fueling. As you can see, it's very delicate operations to unpack the spacecraft and mount it on the test fixture. So at this point, obviously, the spacecraft arrived with the single-access antennas furled for shipment to the Cape, and then also will remain stowed until while we were encapsulated and then deployed after we separate from the Centaur on orbit. But you can see the two single-access reflectors folded one inside the other there. And here, of course, you can see the two halves of the payload fairing being encapsulating the spacecraft. And then we rolled out about a week ago, a little more than a week ago. We rolled out from Astrotech and were transported to the VIF. And you saw the footage that Tim showed of us being hoisted and then made it on top of the Atlas Centaur stack. So things have been going very well since we arrived on December 18th. The spacecraft is ready, and I've got one more clip to kind of fill in the gaps. Tim or Vern showed you the sequence to up until TDRS spacecraft separation. So now we've got one animation that kind of shows you what happens after that, which is interesting, I think. So as I mentioned, after we separate from the Centaur, the first thing that we do is unfold the single-access antennas so they don't take a set. They're composite fiber that Boeing designed for this mission back on HIJ. And here you can see the single-access. Well, first thing you saw was a solar array, one solar array being deployed, and then the two single-access antenna booms, and then the second solar array. And following that, right now what you see is the forward Omni being deployed, and then the last deployment that you're seeing is the Space Ground Link antenna, which is the antenna that points at White Sands, New Mexico, where our ground station is. The two large single-access antennas are the high bandwidth channels that we have to user spacecraft, such as the space station, space telescope, and those are gimbaled and they track the users to allow for the high bandwidth data connection that we provide. So that said, we're excited to go Wednesday. We're ready, and following our successful launch, we've got about a 10-day transfer orbit until we get to geosynchronous altitude. During that time, we're controlled out of the Boeing Mission Control Center in El Segundo. Following deployments, we hand over to the TDRS ground station in White Sands, New Mexico, and from there we do about 3 months of on-orbit test and calibration. Following on-orbit test and calibration, there will be an on-orbit acceptance review, and then the spacecraft will be drifted to its operational location. But it doesn't end here. What's coming up next for our project and our Boeing teammates are we're finishing up the TDRS-L spacecraft. It'll go into storage within the next 2 months, and we'll be back here hopefully about a year from now, launching on another Atlas V mission to launch TDRS-L. And we continue to work towards TDRS-M, and we're ready to go with TDRS-M in December of 2015. So thank you. Thank you, George.
Thank you, Jeff. And I'll look now at Wednesday's weather. Launch Weather Officer Joel Ciambiolo from the 45th Weather Squadron. Joel?
Thank you, George, and good afternoon, everyone. This time of year, as far as weather systems affecting Florida, the main things that we track are cold fronts that typically, on average, move through the state, roughly every 4 or 5 days. And when we're approaching a launch campaign, obviously the timing of these cold fronts moving through the state directly impacts what kind of weather we can anticipate. This mission is no different. We will be tracking a cold front. Right now, if you can see the satellite picture, basically that the system well up to the northwest of that picture is really the entire weather system that will basically be organizing and pushing a cold front through us. And right now, the timing of that cold front, again, timing is critical when we are comparing it or approaching a launch. Right now, the timing of this front has it moving through the area on a very early morning hours on Thursday after the launch window. Now, during kind of starting on Tuesday, as far as the rollout to the pad, what we can expect in terms of our local weather conditions will be very similar to what we're seeing today. We're going to see breezy southeasterly winds. Could be an isolated shower or two in the area tomorrow, but we're not really anticipating any significant weather impacts as far as rolling out to the pad. Moving on to Wednesday during the day, again, that cold front that I mentioned will be approaching the northwestern portions of the state. and we'll be over north central Florida during the afternoon and evening hours. With that, our local weather conditions will continue to be breezy. The winds will be shifting on a kind of compared to what they are now, they'll be shifting in a clockwise fashion to more of a south and southwesterly direction on Wednesday afternoon. Again, we could have a few showers pop up ahead of the main frontal band during the afternoon hours on Friday or on Wednesday and Wednesday evening. But right now we're looking at a 40% chance of having one of our weather rules being violated during the launch window. Again, we're not anticipating the frontal passage until after the launch window, until after midnight, early morning hours on Thursday. And again, we'll be tracking all the weather out ahead of that front. So to be a little bit more specific in terms of weather conditions during the launch window, again, we're going to have a couple cloud decks, a low scattered deck at around 3,000 feet, and a more broken overcast type deck at around 26,000 feet. The visibility should be good. The winds will be breezy. In fact, it'll be windy on Wednesday. The wind direction will be 190 degrees, which is just slightly southwest of due south, or slightly west of due south. And right now the forecast is for 24 knots with gusts up to 28 knots during the launch window. For your information, the launch wind constraint based on that wind direction is 33 knots. There will be some isolated showers in the area. Again, we could have some showers pop up ahead of the main frontal boundary, which again is not expected until after the launch window. The temperature during the window will be around 70 degrees. And again, as I mentioned, we're looking at a 40% chance of having one of our weather rules being violated. The two main rules we'll be going to be watching is the cumulus cloud rule and the disturbed weather rule. Those are the two natural and trigger lightning constraints that we'll be watching. And also in terms of ground winds. Again, it will be windy that day, but based on the direction, we're not anticipating a ground wind violation. Again, the front moves through after the launch window, and if we do need to go into a 24-hour slip into Thursday evening, the front, again, will be well to our south. The main issue on the next day will be the winds. It'll still be windy, but the key there is that the wind direction will be more out of the north and northwest. Now, from that direction, the wind constraint is only 25 knots. And because of that, and we could have some lingering post-frontal thick clouds in the area, but the main issue for the next day, if that were to be needed, would be the ground winds. There's a 60% chance that we would have a ground wind violation for the 24-hour slip, as our forecast for the winds that day will be 20, gusting up to 25 knots with a wind direction of 350 degrees. And again, the wind constraint for that day is 25 knots, so there is going to be that threat. And it will be cooler the next day, hence the cold front move through. It'll be in the low to mid 60s. So with that, again, in summary, we're going to be tracking a cold front. Hopefully things will go as scheduled and we'll be able to beat the front through. But again, that's the thing that we're going to be tracking throughout the day on Wednesday into Wednesday night. Thank you. George?
Thanks, Joel. And we're ready now to take questions. Please give your name and affiliation when the microphone gets to you. And we'll start here in the front with Marcia.
Marcia Dunn, Associated Press. A couple of questions for Mr. Gramling. Are you going to be putting this newest TDRS into service? Will it be a spare? What are your near-term plans for it once it's in its proper orbit and checked out?
I believe the near-term plan is to drift it to 171 West, where it will be put into service for some period of time and tested with users for a little while longer. And after that, I think will be reevaluated at some point, and whether it stays in service or it goes into storage as a backup.
When will that be? When will it be going into service? How many months after launch? Or
we complete our on-orbit test program about 3 months after launch, and then we would begin operations to drift it to, like I said, 171 West, where we would put it into service for some period of time to test with users. I imagine within 2 or 3 months after that, a decision would be made about whether it stays in service or it goes into storage.
Right, and I saw in the press kit that the TDRS-K and L plus the White Sands modifications cost about $715 million. Could you sort of break that down to the specific satellite if possible?
So for TDRS-K, the portion of that is about 350 to 400 million. That doesn't include launch vehicles, but it depends on how we break out the non-recurring cost and spread it between TDRS-K and L, and how we account for project office costs. But it would be somewhere in the 350 to 400 million range.
The rocket, or it does?
I'm sorry?
The rocket cost, I'm
No, that
sorry.
doesn't include
Does not.
launch
All right,
vehicle
thank
cost.
you. Thanks.
Additional questions? You over here, Bill?
I know this is Bill Harwood, CBS News. I know this is probably spelled out in the press kit, obviously, but again, a teacher's question. I remember when the first one went up way back when, aboard Challenger, I guess, and then you've had this series since then. Is there a way to, in lay terms, to talk about the capability of this vehicle versus the originals, or are they pretty much roughly the same now compared to then?
Sure. So you're right. We launched the first TDRS back in 1983, and the first 7 were launched on the space shuttle. The last space shuttle launch was 1995. That was F7. So that version of the TDRS, if you will, was fairly similar to what we're flying today. We had the the 2 single access antennas that had S-band and KU band, and then we had the S-band multiple access phased array. When we got to the HIJ series in 1995 was when we awarded the contract. The only change we made was we added Ka band services to the single access reflectors. So that's a higher bandwidth service, and we continue to fly that service on the Ku spacecraft that we'll be flying this week. The other change that we made from the HIJ series, or the change we made from the HIJ series, was on the 1 through 7 spacecraft. We did the beam forming for the return S-band phased array antenna on the ground. On HIJ, we departed from that architecture and we did the beam forming on the spacecraft. Well, there have been novel uses of the system that have evolved over time, and one of those novel services was a demand access service. And it turns out to do the demand access service, we need to form the beam on the ground. So for the KLM series, we've reverted back to ground-based beam forming for the S-band multiple access return system. You're welcome.
Any other questions here? I think we have one on the line from Marion Kramer from Space News. Go ahead.
Hi. Yeah, this is Miriam Kramer of Space.com. I am mostly curious, so how many TDRS satellites have been in orbit? How many are still in orbit? And what is the life expectancy on the oldest one at the moment?
So this is Jeff Gramling again. Like I said, we launched the first one in 1983. The design life of the first TDRS spacecraft, and those were TRW spacecraft, now Northrop Grumman. 10-year design life. Beginning in HIJ, it's been a 15-year design life. TDRS F1 actually lasted 27 years on orbit, so that has been retired for a few years now. And we've since retired one other TDRS spacecraft, F4. So of the 10 we've launched, we've retired 2, and all of the F1 through 7 spacecraft have lasted well beyond design life. F3, I'm not sure I remember right off the top of my head what its predicted end of service date is, but like I said, we're well beyond design life. And that's been good for us. I'm not sure if I answered your question completely.
No, you did. That was great. Thanks a lot.
Any other questions here in the newsroom? Marcia.
So I'm wondering, when will it be renamed to TDRS 11? At what point will that be?
I believe the convention is, and I'll have to check on this, is once we accept it on orbit and put it into service, we would start calling it F11.
Any additional questions? All right, in that event, a couple of programming notes. You can follow the launch as we go along on Twitter on hashtag TDRS, and on the web at nasa.gov/TDRS. And our launch coverage on NASA TV on Wednesday will begin at 6:15 p.m. Eastern Time. And we'll conclude now. We'll wrap up the briefing and go to a programming feature on space tracking. And thank you very much.
"30 years ago, NASA launched into a new era of high-bandwidth continuous space communication with the Tracking and Data Relay Satellite, TDRS. Today, NASA is continuing this legacy by launching the first of the next generation of satellites, TDRS-K. At Cape Canaveral, the TDRS-K spacecraft sits atop an Atlas V rocket, ready for launch.
3, 2, 1, and liftoff of the Atlas V rocket carrying the next generation and tracking and data relay satellites, TDRS-K.
After a 4-minute burn, the Atlas V main engine separates from the Centaur engine and drops back to Earth. Shortly after separation of the main engine, the protective shield that covers the payload, called the fairing, separates to reveal the TDRS-K spacecraft. After boosting the spacecraft to geosynchronous transfer orbit, the TDRS spacecraft separates from the Centaur engine. Shortly after this separation, the two folded single-axis antenna reflectors are released to take their natural parabolic shape. Once arriving in geosynchronous orbit, the spacecraft starts its deployment sequence by unfolding the first solar array. Next, the two single-axis antennas are deployed and locked into position. These antennas are designed to track and communicate with low Earth orbit satellites. After the single-axis antennas are secured into place, the second solar array starts to unfold, and the SGL and Omni antennas are deployed. Once TDRS-K completes this deployment sequence, it's now ready for a 3-month period of testing and calibration before being placed into service. With this addition of TDRS-K and the upcoming launches of TDRS-L and M, NASA has assured the future of continuous space-to-ground communication.